Hey, this is my lab 3 on black holes and orbits. So the purpose of this lab is to analyze the star's motion, to find the net force on the star, determine the mass of the black hole, and find the initial velocity the spaceship needs to have when leaving the surface of the planet. Just a preview, the main result of this lab was the mass being 1.65 e to the 34 kg and the initial velocity being negative 7.32 e to the 6, 9.6 0 e to the 6, 0 meters per second. So the physics principles and equations that we used were Newton's second law, which relates the net force to the rate of change in momentum, and I also used the velocity update and position update formulas, which simulate like the loops and the updates of the simulation, alongside the universal law of gravitation, as you can see in the bottom, to calculate the attractive forces between the planets and the spaceships and the black hole, etc. So the procedure that I used, I first calculated the mass of the black hole, then I found the necessary speed of the spaceship to orbit without crashing, and then I observed the gravitational effect. So for part 1, the system was the black hole, the surroundings were the star and space. The star mass, as given by the equation, was 2.0 e to the 30 kg, and the gravitational constant. So I found that the black hole mass was 1.65 e to the 34 kg. And if you can see here, this is my code, and I used the different formulas that I listed earlier based on Newton's second law to calculate this black hole mass. I computed the initial and final momentum, so that way I can use the law of gravitation formula and the magnitude of the net force to solve for the black hole mass. And that is what the output of the glow script calculations were. And for part 2, we were focusing on the spaceship and the planet, and so the system was a spaceship and the surroundings were the planet, space, and the black hole. The star mass is the same, and then we use the black hole mass as well. In this loop, I had to calculate the individual gravitational forces acting on the spaceship, and so applying Newton's second law, I was able to continuously update their velocities and positions of the planet and the pull from the moon to create the orbital trajectory that you see with the blue and the magenta. And this was my code that I used to make this orbital loop, as you can see right here, and that was allowing me to project this loop that took a while. Okay, for possible errors, there are a few sources of potential errors. For instance, there was trial and error for initial velocity. There wasn't an exact calculation, it was just more of me plugging in stuff and trying to figure out and getting as close as I can, especially with the time intervals. I feel like the smaller the time intervals were, the more specific I could have gone. But I was having to make a lot of assumptions as well for number 2 about the location and the forces. We assumed that the planet was stationary, which in many cases it's not, and that those were the only forces acting on the planet or the spaceship, which is obviously not true in a real world scenario. So for the what if questions, what does it mean? So for perpendicular versus parallel, perpendicular components only changes the direction of the momentum, while the parallel component changes the magnitude or speed. So the net force is the sum of all forces. Change in momentum depends on the speed and acceleration, but the overall change is easier to observe when we're looking at the change in momentum versus the net force. And then for the second question, the what if, to predict the entire system's motion, you have to include the planet's own motion. So in this case, the planet could be moving and orbiting something else as well. And the initial assumption was that it was stationary, which limits the accuracy of our calculation, which I talked about in the errors earlier. So the spaceship has, and just for what is the most dominant forces, the spaceship has the least dominant force because of its extremely low mass, but also the other forces have larger masses like the black hole, so that would have more of a dominant interaction and force. And that was my lab.